Okay, so today I'm going to talk about how do you find the maximum and minimum points of a function of two variables. Now, why would we be interested in finding something like what does it mean to be a local extrema? Let's say you're hiking. You're standing on the top of the mountain with everything that you see around you, at least in a limited radius. Everything is below you, right? So this is what we call a local maximum. So we might want to know, given a function, what are the local maximums and minimums of that particular function in a given region. So step one is to look for possible candidates, right? And you might remember from your single variable calculus, let's say this is your local maximum, you'll see that at that point, you also have a tangent that is completely horizontal. And similarly, if you have a point where you have a local minimum, you have a tangent that is completely horizontal. What does a tangent mean in your two-dimensional function that lives in three-dimensional space, right? What I'm really asking for is I want the partial derivatives with respect to x and with respect to y is equal to 0. Now let's take a look at what this looks like. If I'm going to look at the slice where one of the variables is constant, and if I just vary the other variable is first increasing up to that certain point where you have the maximum, and then it starts decreasing. At that particular point is that the derivative with respect to x must be 0. And similarly, if I was to keep x constant and just vary y, so now I'm looking at a slice in this direction. When I keep x constant and when I change y, whether you look at the slice in the direction of x or whether you look at the slice in the direction of y, you see that in both cases it's the maximum. And this is cool because this is just single variable calculus. We already know how to do this. All we need to do is we need to take the derivative and set it equal to 0. That means what I need is I'm looking for a place where the partial derivatives, both with respect to x and y, is equal to 0. Okay, we actually have a special entity which we call the gradient. That if we want to look for candidates of where we could have these local maximums or minimums, all we need to do is we need to take the gradient and we need to set it equal to 0. There is one slight problem though. If we just take the gradient and set it equal to 0, it gives us all the candidates for maximums and minimums, but it doesn't really tell us which possible point is a maximum and which possible point is a minimum. Also, we could have this weird thing happen like the saddle. So this is what we do next. We use something called quadratic approximation. So in one-dimensional single variable calculus, we take a function, so like x squared, or graph of that function looks like, it's just going to be a parabola. Right? So if I want to know whether something is a minimum or something is a maximum, all I have to do is I have to try and say, okay, let me try and approximate a parabola at that point. And if the parabola is going to be facing up, that means that the function at that point is also going to be facing up. And so I probably have a minimum. And if I put a parabola at that point and if it's facing down, then that means the function also is facing down. And so it's probably going to have a maximum. So we're going to do something very similar, except what is a parabola of two variables? Now you have x squared and you also have y squared. So let's look at the four possibilities where I could have x squared plus y squared minus y squared minus x squared, and negative x squared minus y squared. I'm going to first look at the possibility where both x squared and y squared have the same sign. So if x squared and y squared are both positive, x squared plus y squared looks like, well, you guessed it, a paraboloid, because we've looked at this several times this semester. And if you have negative x squared minus y squared, well, then that's just like putting a negative sign to the entire paraboloid. So this is going to take the paraboloid and just face it downwards. The problem is if you have x squared minus y squared. If you take a look at this graph, as you can see, it looks like this weird looking thing that extends in all directions. But if you zoom in at what's happening at the point 0, it looks like a saddle, where on one side, it looks like it's a minimum, and from another angle, it looks like it's a maximum. And similarly, if you take y squared minus x squared, well, now you just have a different saddle. But this is good, right? Because we found out that all we need to know, if x squared and y squared have the same sign, then it's going to be a parabola. And if x squared and y squared have different signs, then it's going to be saddle in the middle. So how do we figure out what this x squared and y squared are? This very, very long formula to figure out what the quadratic approximation of a function is. And the equation of a typical quadratic function looks like that, okay? And in this, the coefficients that matter are all the coefficients that have to do with just the quadratic parts, right? So what are the quadratic terms? There's x squared, there's xy, and there's y squared. So these are the three terms we're going to look. You'll see that they're exactly the second derivatives of the function. So as you can see, the coefficient of x squared is fxx, the coefficient of y squared is fyy, and the coefficient of xy is fxy. It's kind of nice that they all sort of match, right? I'm going to make a different video about how do the quadratic functions actually tell you whether they're hyperboloids or paraboloids, but right now you're just going to have to believe me when I say this. Let's take this ugly function and let's make it a much simpler function. We'll call it ax squared plus bxy plus cy. Specific term that has to do with the coefficients of this function, we'll call it 4ac minus b squared. And we're going to call this the Hessian matrix. So we'll call it h of xy. If this 4ac minus b squared is positive, you have a chance of getting a paraboloid. So if 4ac minus b squared is bigger than 0, then you have a paraboloid. We don't yet know if it's going to be facing up or facing down, but we do know that it's going to be a paraboloid. Now, if this Hessian is negative, then you know that it's actually going to be a saddle. So sounds simple enough. Let's take the 4ac minus b squared and let's go back to our quadratic expression. 4 times 1/2 fxx, 1/2 fyy minus fxy squared, which is just fxx, fyy minus fxy squared. And if this particular entity is going to be positive, then we're going to say that it is going to be a paraboloid. And if the Hessian is negative, we're going to say that it is going to be a saddle. So now it reduces us to just this case. We find the second derivatives, you calculate what fxx, fyy minus fxy squared is. And all you need to do is check whether it's going to be positive, negative. We have figured out whether at that particular point we can fit a paraboloid or whether we can just fit a saddle. Great. Let's say that you actually found out that you can fit a paraboloid at that point. How do you now know whether the paraboloid is going to open up or whether it's going to open down? So in order to do that, you're going to have to look at the coefficient A, because the leading coefficient, if they are both positive, then you're going to have a paraboloid that faces up. And if they're both negative, you're going to have a paraboloid that faces down. So A and C are going to be positive if fxx is going to be positive and fyy is going to be positive, but we're just going to look at one of them because remember, for a paraboloid, they're both going to have the same sign. So it's okay to just look at one of them. And if they're both going to be negative, you have a paraboloid that is facing down. You are able to fit a paraboloid that faces up. At that point, you probably have something that looks like a valley or a minimum. So let's recap. We want to first start by taking the function and looking for all the possible candidates that could be local maxes or local mins. And unfortunately, when we do this, we also end up with a bunch of points that could be saddles, because we basically look for all the points where the gradient is 0. You're going to come up with possible maximums, possible minimums, all local, and possible saddles. Now we have to examine at each point individually whether you have a max, a min, or a saddle. How do we do this? We're going to start by taking the second derivatives, and then we're going to calculate the Hessian goddess, who we are going to say is fxx fyy minus fxy squared. Because you calculate this expression, it's going to give you some function, that's the Hessian matrix, and then you want to evaluate the Hessian at your critical points. So really it's just the Hessian being positive or negative, but you have to calculate the Hessian first separately, and then you have to evaluate the Hessian at these different points. And that's what's going to tell you if the Hessian is positive, it's going to tell you that you have a paraboloid, so you have a chance at getting a max or a min. And if the Hessian is negative, it's going to tell you, nope, no luck, you're going to have a saddle. Okay, if it's a saddle, we don't really care because that's not a candidate for a max or a min. But if it's a paraboloid at that point, so basically if the Hessian at a particular point is positive, then we actually care about what's going to happen next. But make no mistake, if the paraboloid is facing up, that means if fxx is positive, that means you actually have a minimum at that point. And if your paraboloid is facing down, that means your a is negative, or your fxx is negative, that means your paraboloid is facing down, so you have a maximum at that point. Let me put on lipstick and then I'll continue. One more time. Find the critical points by setting the gradient equal to 0. Find the Hessian fxx fyy minus fxy squared. Once you find the Hessian, evaluate the Hessian at each of the critical points that you found. If the Hessian is positive, you have a chance at getting a paraboloid or a max or a min at that point. And if the Hessian is negative, that means you have a saddle at that point. You can now fit a paraboloid at the point. Is the paraboloid going to be facing up or is it going to be facing down? If it's facing up, then that means your fxx will be positive, so then you get a minimum. And if it's facing down, your fxx will be negative, so you get a maximum.
That's all, folks.